Okay, so the last lecture was about general properties of algebraic cycles, definitions of the Chow groups, and so on. And apart from a brief occurrence of the exponential sequence, there was no complex geometry at all. So this talk, I'm going to review some facts about Hodge theory, talk a bit about the Hodge conjecture, which is, I guess, in some ways the most celebrated conjecture in the area, and begin to talk about what is going to be the main subject of the next lecture. That's tomorrow's lecture, which is going to be on mixed Hodge structures and intermediate Jacobians and Deligne cohomology. So, okay, so let me just begin by recalling the basic results of Hodge theory for, first of all, for a smooth projective variety x over c. Now, I may live to regret this, but I think I probably have to distinguish between x, which has the Zariski topology, and the associated analytic space I'll just call xn, which is just the underlying complex manifold with its classical topology. Now, it's already come up in Francis's lectures, for example, that we know that if we take what he calls the Betti cohomology of x, say with real coefficients, which is just the cohomology of the analytic space, singular cohomology, for example, and that's by the Durham theorem. That's the cohomology of the complex of C infinity forms. So A n x is C infinity real. Maybe I'll put an R down here. R valued n forms. And we'll also have the ones with complex coefficients. So these are C-valued. And we know that there's a type decomposition here, so we can write any n form as a sum of PQ forms where I guess I don't have to write down, we have P dz's and Q dz bars. That's the standard type decomposition. And the Hodge theorem is the statement that this decomposition passes to cohomology. So this, of course, has the exterior derivative d to an plus 1. And here we also have a d, therefore can be broken down into two types, where d is of degree by degree 1, 0, and d bar is of by degree 0, 1. And then we have the Hodge theorem, or Hodge decomposition. So if we define HPQ of x to be the cohomology classes which are representable by, which should I call this? My notes say alpha, which are represented by PQ forms. Modulo exact ones. And then the statement is that Hn of x with complex coefficients is the direct sum of these subspaces PQ and this is the subspace of Hn and is equal to the complex conjugate, rather obviously, of HQP. So in other words, and this says this and no more than this, well, so if d omega is 0, then omega is cohomologous to a sum of closed PQ forms. So it's can you write it as d beta plus sigma alpha PQ in our PQ forms, and they're closed. Okay, it is not the case that if you take omega, which is closed, that its PQ components are closed, but it's cohomologous to something whose components are closed. So that's the Hodge decomposition. Sorry? Ah, thank you. And of course, because this is equal to 0, and because these have different bar degrees, that of course is equivalent to saying that both d alpha pq and d bar alpha pq are 0. Okay, and the proof of this is by hard analysis, which is showing that every cohomology class has a unique harmonic representative, and that the harmonic forms decompose into PQ forms like that. Okay, so this is the transcendental part. There's algebraic consequences of this, which are almost as useful. So for this we need the Durand complex. So we had, again, I think in Francis's lectures, the algebraic Durand cohomology has occurred various times. So there's a standard resolution of the constant sheaf C on X analytic given by the holomorphic Durand complex. So this is exact by the Poincare lemma, holomorphic Poincare lemma, so omega R X analytic here is holomorphic, the sheaf of holomorphic R forms. And so that leads to the comparison isomorphism, which has already occurred. But this is therefore isomorphic to, by this resolution, the, okay, well, I'll write hypercohomology, although I always think that's a bit silly to give it a special name. So it's the cohomology of this complex of sheaves. So that's the analytic Durand cohomology. But then because this is a projective variety, then by the Gaga principle, this is the same as the hypercohomology on the variety with the Zariski topology. of the complex of the algebraic de Rham complex. So implicitly I mean differential forms over C. So this is by definition the algebraic de Rham cohomology of X over C. And then this complex in either incarnation has a subcomplex Fp, which is just the truncation, or the stupid filtration as people call it. So we just start at omega p and then just carry on. Okay, so this is the Hodge filtration on this complex, and then it follows from the Hodge theorem, plus some easy homological algebra, that let's call this statement 1, that for all n and p, if we take the cohomology of this subcomplex, that injects into the total cohomology, into the de Rham cohomology. Or equivalently, is easily seen to be the same thing, called 1 prime. So this is there's a filtered complex, so we have a spectral sequence associated to it, the so-called Hodge de Rham spectral sequence, or the Fröhlicher spectral sequence. So the graded piece here is just omega p, so it's just this thing here. So this spectral sequence degenerates at E1. And then the image in one of this, this is by definition, let's put the colon there so it's this way around, is by definition to the Fn of the Hodge of the de Rham cohomology, sorry, Fp, and that is then equal to just the sum over p prime greater than p of h p prime n minus p prime. This is the Hodge filtration. And then we also get that HPQ is isomorphic to the cohomology of the locally free sheaf omega xp. And so putting that together, maybe I'll just write one line here. So in particular we get the following statement, which is that dimension of the de Rham cohomology is just the sum of the dimensions of these Hodge cohomology groups H, Q, X, omega P. So the statements 1, or equivalently 1 prime, and 2, they're purely algebraic statements. So 1 and 1 prime and 2. So they're pure algebraic statements. And for a long time, people wondered whether there was a purely algebraic proof of this, which there is. Well, it's an arithmetic proof, really. Well, it's an algebraic proof, I suppose. Which was found by Deline and Elzy in the 80s. And it's a reduction mod P, or more precisely, it's a reduction mod P squared proof. So they prove a very beautiful theorem that the Hodge-de-Rham spectral sequence for a variety in characteristic P degenerates if and only if you can lift the variety to mod P squared. And then by some fairly easy but tedious reductions, if you start with a variety of a C, first of all, has only a finite number of coefficients in its defining equations. You can therefore define a finitely generated extension of Q, so it's defined in fact of some finitely generated Z algebra, and then you can specialize, and then eventually you reduce to the case of that's treated by Deline and Elzy. That doesn't quite give you the full Hodge theorem because you don't quite understand the action of complex conjugation. But for many purposes, particularly for defining periods, all you care about is the Hodge filtration. Okay, so since I'm going to define mixed Hodge structures shortly, it's probably as well just to say what we have here axiomatically. So formally, what do we have? We can define a pure Hodge structure maybe I'll just do it directly. I'll just do this with a pure A Hodge structure. Where A is going to be Z or Q or R to be of HA, which will be a finitely generated A module. So in the case when Z, torsion is permitted, and then plus a decomposition and this will be pure A Hodge structure of weight N plus a decomposition of HC, that's just H tensor with C, HA tensor over A with C, as a direct sum. So we allow negative indices here, but P plus Q is N of some subspaces HPQ satisfying HPQ equals HQP bar. So these things form an abelian category in a pretty obvious sense. Morphisms, just morphisms, which are compatible with these decompositions. And you can also form a tensor product if we have H, which is of, so call H the whole collection. So we have H of weight M, let's say, and H prime of weight N prime. Then if we take H tensored with H prime, then there's an obvious way to make this into a Hodge structure of weight N plus N prime. And the maybe I shouldn't call it Z. Let's call it ZR. ZR is the Hodge structure. It's the Z Hodge structure. And I think this has been already arisen. So with integer lattice is 2 pi I to the R Z. HC is therefore just C, and that's equal to H minus R minus R. So that's a pure weight minus 2R, and then one has the Tate twist functor for any H. This is just the tensor product with ZR. R, any integer here. And so what the Hodge theorem can just be restated as saying that the cohomology of X has a natural Hodge structure in degree n. It's got weight n. Okay, so now let's see what's next. Okay, so now I just want to revisit briefly the exponential sequence from the last lecture. Okay, I'm going to drop the ands because they're going to be an everywhere. So I'll just forget about the classical topology. And then recall that gives us a cohomology class map from the Picard group, which is just the cohomology of OX cross, to the integer cohomology, and there's this one twist here. And then the next thing that I didn't write down is H2 with coefficients in OX. So that, staring at what's over there, is the same as the complex cohomology modulo the F1 in the Hodge filtration. And the image of this map is the Néron-Severi group. And so you then get, and this is the Lefschetz theorem, or one of the Lefschetz theorem. Is that the cohomology class map identifies the Néron-Severi group with the kernel of this, so it identifies it with the cohomology classes, the integer cohomology classes, such that C, the image of C in the cohomology with complex coefficients lies in, so it has to map to 0 in F1. On the other hand, it's integral, so it also will map to 0 in F1 bar, so it will have to line H11. Because that's F1 intersect F1 bar. Sorry? There is a slightly annoying thing here, yes, that I have sort of shifted the weight here.
Where does F1 bar come from? It looks like F1 would be okay.
Yes, but if it's in F1, it's also in F1 bar. And F1 intersect F1 bar is H11. No. No. Here you get it's in F1, but F1 if it's but because it's also in here, this is invariant under complex conjugation, so it therefore also lies in F1 bar. Lefschetz would not have liked that. No, I'm certainly abusing notation here. Here I'm just thinking of this as being cohomology with values in 2 pi I z, not the Hodge structure. Hopefully I will try and confuse the audience even further in a few lines' time by doing the same thing. Now, it's worth noting...
Sorry.
Yes?
Could you please explain some more details about the morphisms?
Ah, yes. The morphism. So, yes, that's a perfectly good question. So, what are the morphisms? So, this board, I think, is overdue to be erased. So morphisms are, so I have an H and an H prime, so then I have to have an F from HA to H prime such that FC, which therefore goes for HC to H prime C, maps HPQ to maps this to H prime PQ. Okay, it's really the only possible definition, I think. Now, one consequence of this Lefschetz theorem is that every torsion class in here, well, that's automatically dies in here, so it's automatically the condition on the right is vacuous. So in particular, every torsion class in H2 is algebraic. And there are standard examples of algebraic surfaces which have non-trivial torsion classes. So, see if I can get this right. So the standard example, which I believe is possibly a generalization of a Godot surface, is where you start off with some diagonal hypersurface. So x0 to the d. There's going to be a surface, so there'll be x3 to the d equals 0 inside P3, and d has to be greater than or equal to 4. And we act on this by group of d-roots of unity by sending point with coordinates xi onto the point with coordinates zeta to the I times xi. And if d is greater than or equal to 4, this is actually a free action. There's a free action. And then if you look now at the quotient, x modulo the action, this is an algebraic surface, which is smooth, so it's a non-smooth surface, projective. And it's not hard to compute its H2 with integer coefficients. Sorry, let's call this hx prime, so I don't have to grab anything out. And the H2 of this is the, well, that's not compute, that's, okay, so it contains, I think, let's see what I want to say here. Okay, let's just say, so this contains, all I want to say is it contains z mod dz. So that's an easy way to construct surfaces with torsion in their H2.
In that case, can you realize explicitly algebraically?
The class.
No, but the class should be algebraic. Can you realize by an explicit cycle in this case?
Actually, I don't know the answer to that, but maybe somebody who's more geometric in the audience does. To write down an explicit cycle.
Well, more generally, is this
Yeah.
effect? In other words, if you have a torsion class, can you actually construct effectively cycles like that?
Well, I'm not quite sure what effective means in this
But
context.
you have an output, you can
Yes,
put down the
yes.
equations for the cycle just by following through the proof. Is this theorem effective in the sense that in actual case for a torsion cycle, I can find representative? Seems to mean something.
Well, it looks as if the you can. Yes, I believe it is actually, in the sense that, I mean, okay, I may well, yeah, because I think you can explicitly write down a cocycle here, and therefore you can explicitly write down a line bundle, and then you take a meromorphic section of that, and that gives you a cycle. That's probably about as effective as you can hope for. No.
If the section is effective,
Yeah.
it's explicit, then yeah.
Okay. I've never done any serious computational algebraic geometry, but I'm sure there's somebody in the audience who knows how this.
Can you please explain why torsion means algebraic?
Ah. Because this is a C-vector space, so any torsion element here dies in this exact sequence, amounts to 0 here. Yeah. So the Hodge filtration has nothing to do with it, therefore. So in the last lecture I mentioned the definition of the cohomology class of a cycle of arbitrary codimension. So let's suppose now we have a codimension P cycle, then it has a cohomology class so it even has a cohomology class with integer coefficients. So let me try and write down a possible definition for this. So it has one with integer coefficients twisted by p. So let's write down the definition. We only actually have to assume that z is actually a subvariety and then apply linearity. So, okay, I'm not sure this is the best way to do this, but well, let's first of all take out the 2 pi i's, which everybody wants me to take out, but I insist should be there. Okay, so this maps to the cohomology with integer coefficients, and now by Poincare duality, that's isomorphic to the homology, I guess, in dimension h2n minus 2p of x. And this, of course, depends on a choice of orientation. In other words, depends on which square root of minus 1 you choose, or which, equivalently, which orientation of c you choose.
Isn't that canonical if it's convex? The projected convex drag, you have to canonical.
Once you've oriented c. So you have to decide whether I is up there.
He was oriented by gals.
People have tried very hard to disorient C.
Even then you have a choice for product orientation.
There's an advantage of not fixing an orientation, which is that, for example, if you take the complex conjugate of your complex manifold, the constructions you get are invariant under complex conjugation. Here I've chosen, yeah, I'm going to put it back in again in a moment.
I think we talk about C, fixed C, C is not an abstract.
When we grew up, I know, Don, when we grew up, we thought that C was the reals plus I times the reals, didn't we?
It is. And that there are two choices how to
Yeah.
C is.
Definitely for periods, you should put the 2 pi i's in. So anyway, this is a predictable but diversion. So we obviously have the map from the homology of Z here, and this is the highest degree homology. So again, choosing an orientation here, we can identify this with Z. So this is also depends on orientation. I'll put ditto there. And now 1 is what's supposed to map to that. Now, if we were to choose a different I, then this would, of course, change by minus 1 to the p. This would change by minus 1 to the n. And this would change by minus 1 to the n minus p, because this has complex dimension n minus p. And so all the minus 1s would cancel out. So the definition is the same whichever square root of minus 1 you choose.
I mean, why do you end up in this case? If I replace 5 with some other number, still it's isomorphism, but it's not a true.
Well, this is definition.
Oh, you just define it.
Yeah, this is, I've defined it by this commutative square.
Oh, so you could also put Z as something else.
Well,
You could put Z as 7p.
I suppose you could put C at 7p. I'm not sure that would be a very good idea, though.
I know it's not. You have to really explain how this is happening.
Well, also, I mean, again, with the exponential map, you could replace the exponential by exponential of 2 pi iz, which is what some people do, or you could replace it by the exponential of 15 times the square root of 2 times z, times I of z. But I don't think that would be a good idea either. Okay, there is something of a cultural, I'm not sure I would call it a cultural war, but a cultural disagreement between people who think you should put these 2 pi i's in and people who don't. Exactly. When you do arithmetic, yes, when you compare with the tile cohomology, it certainly makes more sense to put the 2 pi i's in. Because the H1 of GM with integer coefficients is most naturally 2 pi iz. Okay, we could talk about this for hours. Okay, now I also mentioned that, okay, so the image of the cohomology class in complex cohomology, H2PXC, so that's just the dual. And now again, there's a 2 pi I here of H2n minus P minus 2P XC. So if I have an eta here, I'm going to map that to 1 over 2 pi I to the n minus p. Sorry, no, 2 pi I to the n here. The integral over x of eta wedge omega. Okay, that's independent also on the choice of the orientation. So the image of this is then the map. Omega goes to, okay, we have these 2 pi i's. Trouble is, if you do number theory and compute periods and things, if you leave the 2 pi i's out in one formula, then they come back to haunt you in another. So it's just the integral of omega over z with, again, with this normalization. Right. Now we come to a bit after time. And I'm afraid I will have to ask James when I started, because I forgot. Right. Fine. I can continue until 25:2. Sorry? I certainly would not dream of pushing it beyond that. Okay, so we now come to the Hodge conjecture. State just for completeness, which is that if we tensor with Q, then this surjects onto, okay, James is going to complain here, never mind. So one obvious fact here is that this cohomology class is represented by a PP form. It's given by an element of HPP of x inside here. And that's just because this integral will be 0 if omega is not a n minus p comma n minus p form. So the Hodge conjecture just says that rational classes, PP classes, are algebraic. Now, what I'm going to write down might be confusing. But I want to write it down because of what's going to happen in the next lecture. I'll just say, in terms of Hodge structures, and one can meditate the weights here for some time. it says that so one way of writing this is just saying that's just the Holmes in the category of Q Hodge structures from Q0 to the Hodge structure H2P X Q twisted by P. So if you sort of disentangle the definitions, and you bear in mind that the twist is supposed to take has got this minus R part in it. That's one way of saying it. So it's just the Holmes from this is the unit object in the category of Hodge structures to this particular Hodge structure. I say that now because we're going to have the X coming up in the next lecture. Okay, now Hodge's original conjecture was the integral version of this. So the analog of the Lefschetz theorem, which would be that I'll just say of type PP, meaning whose image in complex cohomology is PP. Unfortunately, this is false. It's doubly false. For two reasons. So it's false for two reasons. So the first reason is that, unlike the case of divisors, you can have torsion classes which are not algebraic. So there exist non-algebraic torsion classes in general. So this was observed by Atiyah and Hirzebruch. And there's another way, and perhaps more extensive way, to see this due to Totaro. Both of these methods use algebraic topology. And the other fact is that even if H2P, the integer coefficients, is torsion-free, you can have non-algebraic cycles, non-algebraic classes with some multiple, obviously a non-zero multiple, being algebraic. Now, I thought that the examples of this were found by Totaro, but I'm not actually sure who found the first example. The example that I'm going to give now is an example due to Collar, which has the advantage that I can explain it extremely quickly. And there are a number of other examples by other people.
On the degrees and stuff, his argument was flawed, even though it's correct.
Sorry?
His argument is correct, but there are mistakes.
Whose argument?
Colors. In the differential example.
Ah, okay, so maybe I'm going to say something that's wrong.
No, it's just that I explained it to Collier, and he says, oh no, change it to such and such and such and such, and I did that and it didn't work either.
Oh.
But somebody did verify.
Okay, yeah, so for example, this is contained in a paper by Soulet and Voisin.
Jean-Louis.
Sorry? I'm going to give you the example. Yeah, let's give the example, then we argue about whether it's correct or not. So here is what I believe is Collard's example. So you take a prime P, which is at least 5. And then you take D to be P cubed times some D0. Doesn't matter what. So we're going to look at hypersurfaces of degree divisible by P cubed. So we take X in P4, a hypersurface of degree D, and it will be generic. I mean, there's some issue about how generic it has to be, but you can take one that has, you know, algebraically independent coefficients. That's as generic as you can get. Okay, and then Collard's theorem is that for any curve C inside X, the degree of C is divisible by P. Now, why is this a counterexample? Well, you've got a hypersurface. The cohomology of a hypersurface is fairly easy to describe. So the H2 is Z, is generated by the hyperplane section. So I'll call it H2Z. H is the hyperplane class. And then the H4 is generated by some class, let's call it C, where the cut product of C and H is 1 in Z, which is H6. Okay, so, and this is, and H4 with complex coefficients is H22. So there's no Hodge obstructions to algebraicity, but this theorem says that any curve here, so we take the cohomology class of codimension 2 cycles, because every curve has degree divisible by P, and the degree is just the intersection number with the hyperplane, this is therefore contained in P times Z times PC. So in particular, C is not algebraic. Okay, so that's Collard's the theorem that implies this counterexample. So why is the theorem true? Well, you've chosen a generic hypersurface because you can then specialize it to some other hypersurface. And specialize the curve as well. So the idea of the proof of theorem, so this is a bit of a sketch, but so we'll specialize start with X and this curve C to some X0 and C0. So you just, by assigning some values to the parameters, and okay, so it's easy to specialize X. Specialize C, you have to use some property of the some standard Hilbert scheme argument. Anyway, there is a standard argument which tells you because the Hilbert scheme is proper, it's just buzzwords really, that you can specialize this for where now x0 will be a hypersurface, still, P4, but it's going to be a singular hypersurface. So this is the trick, is it's a singular hypersurface, still of degree d, in P4. And now C0, okay, you specialize this as just some one-dimensional subscheme. With the same degree as C. Okay, that's just some routine deformation theory to be able to do that. And now, so the trick is, what's x0? So the choice of x0 is done as follows. So here's a nice way of writing down. So if you start with P4, and we take a smooth degree d0 hypersurface in there, and now we take a map given by some homogeneous polynomials of degree p. And we choose this to be generic and this to be generic as well, these polynomials. So then this will map to some x0 inside P4. And if you make these things generic, this map will be generically one-to-one. This will be generically one-to-one, but this will be singular. So this is just a normalization of it. So it's singular, so there might be some places where it's not one-to-one, and again, by genericity, you can assume that it's 2-to-1 over some surface, and 3-to-1 over some curve, and then over a bunch of points, it'll be 4 over some points. So it's certainly not going to be an isomorphism, but it's a birational it's birational morphism, and okay, so I guess you do this by first of all embedding it into a bigger dimensional projected space so it's still smooth, and then you just do iterated projections. It's the usual sort of argument like showing that every curve can be embedded as a plane curve with nodal crossings. So we have this. And now the point is that this has degree.
Sorry, why is it not one-to-one generic?
Sorry?
Why is it one-to-one generic?
If you think about it, it's obvious. So it's not obvious, no, in other words.
And why, I mean, where's the PQ come from? It looks like there are 5 factors to protect PQ.
Well, because this is dimension 3. That's why the degree. You just compute the intersection with a hyperplane.
Oh, I see.
Okay, yeah. Now inside here you've got your curve C0. Now you'd like that curve to be the image of a curve in here. That need not be the case, because this map is not one-to-one. But it's 2-to-1 over a surface and 3-to-1 over a curve. So that means if you take this curve, you pull it back, and then you take the image there, you'll get some multiple of this. So what you get is, therefore, there exists some curve which I'll call D in Y, such that this map should have been called phi. So if we take the push forward of D as a cycle, well, You might be able to do better than this, but 6C0 is fine. But now you compute degrees. Okay, and then you find that, okay, well, since I'm going to stop, 6 times the degree of C0 is then going to be, because you've got this map phi here, D has dimension 1, you get P times the degree of D. And so since P is greater than 3, that implies that P divides the degree of C0, which is the degree of C. And that's the end. You don't have to ring your bell.
Oh, I really want to.
Oh, yeah, please do. Would you like me to talk for 30 seconds more so you can ring your bell?
Ring the bell, James.
Go on, ring the bell.
This is called the Dan Bell Some Mercy.
Any questions?
No questions? Okay, the speaker again.
That's correct, is it? That's correct, is it?
Pardon?
The argument is correct, is it? This one?
Yes.
Good.